Helix Micro-Rebar is an alternative to rebar. Made up of small pieces of twisted wire, Helix distributes throughout the concrete, providing uniform reinforcement throughout the entire section. Helix is internationally approved and code compliant.
We provide a document called an evaluation report, and it details product attributes that are documented from test reports, calculations, and other supporting data provided by the manufacturer and certified as being produced by an independent third-party agency.
Helix has been used in the field for over 10 years in 30 countries.
I can see how the strength of it is going to be more beneficial than a wire mesh. Wire mesh is just going to be running in one line, where this is going to be creating all kinds of different, reinforcing.
Using the peer-reviewed and approved design method, you can quickly and confidently design with Helix.
From my standpoint, using the Helix fibers as replacement for wall reinforcement has been a great asset to both my clients and my design firm.
Packaged in boxes and palletized for shipping, Helix can be delivered all over the world. At the ready mix plant or on the job, Helix is easily and quickly added to the mix truck. It takes 1 minute or less per box of Helix, and then just 5 minutes of thorough mixing. Helix is placed just like plain concrete. Helix reinforced concrete can be installed using all traditional methods, including pumping and shotcrete. Finishing concrete reinforced with Helix requires no special techniques. It finishes smoothly and easily using standard finishing practices. Helix does not stick up when finished and does not interfere with joint cutting. Helix can be used to replace primary steel in structural and non-structural applications. Helix reinforced concrete is more efficient than rebar or mesh, providing improved performance, increased first crack strength and crack resistance, better durability, and improved shear strength. Replacing rebar or mesh with Helix Micro-Rebar will improve construction site safety by removing the tripping hazard. It eliminates placement errors that greatly reduce the effectiveness of rebar and mesh. Using Helix as your reinforcement saves an average of 20% on the concrete portion of the project, primarily through reduced labor costs. And using Helix will noticeably reduce the construction time. Helix has been providing customers with a better product for over 10 years. We invite you to see how Helix Micro-Rebar can provide your client with a better, safer, more economical product.
I'm Luke Pinkerton, Chief Technology Officer of Helix Steel. My background is in structural engineering, and I've been involved in the concrete industry and Helix for 18 years.
Helix was originally developed as a blast and earthquake-resistant concrete reinforcement. The images shown here are the results of 10 pounds or 5 kilograms of C4. As we know, concrete is brittle. Even 2 layers of rebar spaced at 4 inches or 100 millimeters could not prevent the concrete from shattering under the blast. When Helix is added, the spalling is virtually eliminated.
Fundamentally, Helix works like a composite material. In this case, it allows the concrete to flex under the load, forming many smaller cracks. Simply put, it makes the concrete more ductile without adding cost.
Although blast resistance is a very interesting application for us, it represents only a segment of the projects that we completed over the last 12 years. In this presentation, I will be going over how the Helix Design Method was developed, how Helix is approved for any application, and finally introduce the design method and an example of how it works. The objective is to give you a basic understanding so you can begin to consider Helix for your future projects and take advantage of its superior performance and cost savings. The applications for Helix are widespread. There's really no application where Helix has not been used. Applications ranging from simple slab on grade to slab on metal deck to complex structures like multi-story cast-in-place buildings and foundations. We're particularly proud of the performance savings we've been able to provide our clients like FedEx, Coca-Cola, Pemsmore, ABB, the City of Seattle, Pier 57, Alstom Energy, and Rio Tinto Mining.
Regardless of the application, we can always point to an example of where the product has been used successfully. We're happy to report that over the past 12 years, we've had complete success with no failures.
Let's start with a review of concrete basics. We assume concrete cannot carry any tension, and it must fail before rebar activates. As a result, our job as structural engineers is to find areas where there's tension in the concrete and add reinforcement. We assume that the concrete will crack in these locations, and the reinforcement is designed to carry all the tension. The red stress-strain curve shows what's called elastically perfectly plastic behavior. Instead of failing suddenly like plain concrete, the rebar holds the load even as the strain increases, making reinforced concrete structures more ductile. While steel offers excellent ductility, it comes at a price. First, the concrete must crack for the load to be transferred to the rebar, which can lead to further deterioration or corrosion. Second, the bar must be embedded at least one development length on either side of the crack and must be placed at the proper depth. Ensuring proper installation of the bar at the correct depth with the proper laps is challenging and costly in the field. Helix acts like rebar but on a smaller scale. This is why we call it Micro-Rebar. Like rebar, Helix is made of ductile steel, but Helix begins carrying the load even before cracks form. How? Because it's smaller in size, only 1 inch or 25 millimeters long and 20 thousandths of an inch or a half millimeter in diameter. And because of its twisted shape, it has a high mechanical bond to the concrete. Also, the development length for Helix is 100 times less than rebar. What really makes Helix different is its twisted shape. Look at the green curve on this graph. The curve looks very similar to the red curve I showed on the previous slide. It's elastic, perfectly plastic type behavior. This occurs because Helix must untwist to come out of the concrete. The torsion from the untwisting process is the source of the constant resistance. People have been trying to do this with concrete for centuries. The problem is the behavior of anything you mix into the concrete is fundamentally governed by friction. Friction is just a function of how much surface contact there is between the reinforcing element and the concrete. The blue curve shows the instability that occurs with frictional bonds. This case is a straight fiber with increasing strain.
There are other products that have some deformations on them, but they're still ultimately governed by friction. Often you'll see long fibers that are really designed to maximize the amount of surface contact between the fiber and the concrete. The fundamental difference is that they generate a constantly decreasing amount of resistance as strain increases. You can't design concrete based on an unstable form of reinforcement.
Helix changes everything because it's the first discontinuous reinforcement that offers stable tensile behavior through its untwisting failure mechanism. The main feedback we got from engineers as we brought this product to the market was, well, those are nice properties, but how do we design with it? The fact is, you can design with it much the same way as you design with rebar. To demonstrate this, we ran the standard tensile test, ASTM E111, for rebar on Helix Micro-Rebar. In this test, a tensile machine pulls on a piece of rebar, generating the red stress-strain curve we looked at earlier. To run this same test on Helix, we turned to Element Labs in Minneapolis. Element is an ISO-accredited concrete testing facility. They designed an hourglass-shaped specimen about 24 inches or 600 millimeters long and 6 inches or 150 millimeters in diameter, which we cast using various dosages of Helix. A standard adhesive anchor was installed on the top and bottom of each sample to allow the lab to clamp the specimen into the machine. Precision sensors measure the displacement across the 4-inch or 100 millimeter gauge length.
With this test, we characterized Helix performance and tension the same way that they do with rebar, thereby allowing you to use the same design methods that you've used your entire career.
The results of the testing show both the proactive and reactive phases of resistance. In the proactive phase, Helix actively carries tension. It makes the concrete more flexible and increases the strain it takes to form a visible crack by nearly 3 times compared to plain concrete. After the concrete cracks, Helix provides stable tensile resistance up to 1,000 microstrain as it stretches elastically and untwists. For comparison, structural rebar design only allows up to 750 microstrain. After this, the forces localize around the crack and the crack begins to grow. When the crack gets large, Helix can completely pull out of the concrete, leading to unstable, decreasing tensile resistance. We do not allow Helix-only design in this unstable region. The actual level of tensile resistance and the increase in strain required to crack the concrete depends on the Helix dosage. Let's take a little closer look at the first part of the curve, which we call the proactive part of the curve. With Helix, we actually get a very interesting behavior that we're not aware is possible with any other type of reinforcement. If you look at the two curves, the red curve is plain concrete and the black curve is concrete reinforced with 25 pounds per yard or 15 kilograms per cubic meter of Helix. What we see is a statistically significant reduction in the modulus of elasticity and increase in the strain capacity of the concrete. What this means is that the concrete is actually more flexible and can tolerate more tensile strain before a dominant crack forms. The slope of the red curve is about equal to EC, but when you add the Helix, it decreases the slope with a stable, perfectly plastic plateau. The energy required to form the crack is more than twice that of plain concrete. Just as a reminder, rebar is not active at all until the concrete cracks. The reason this is happening is because Helix has a very efficient bond and just doesn't let go of the concrete. With its twisted shape acting in essence like a screw instead of a nail, it just doesn't allow itself to move. Helix functions at a much smaller scale than rebar. You're getting contribution of the reinforcement even before a dominant crack forms. Once you do get the formation of a dominant crack, you get a region of tensile stability that I talked about a moment ago.
While all this science is interesting, the lingering question is, how, as an engineer, can we responsibly and safely implement Helix in designs where rebar is normally used? This comes down to developing a mathematical model of Helix performance and applying an appropriate factor of safety.
The Load and Resistance Factor Design Method, or LRFD method, provides a standardized framework to accomplish this. It requires us to define functions for tensile resistance and the statistical variation of these functions, select an allowable probability of failure, and finally, provide test data to calibrate the model. This method was originally developed by MacGregor in the 1970s. MacGregor provides a statistically robust method for computing the required factors of safety based on these variables.
The biggest challenge for Helix in this process was managing the large variations in micro-rebar distribution and the limitations on usable strain inherent to the system. The LRFD method demanded that we place restrictions on applications as well as develop a class system based on the consequences of failure for reasonable resistance factors to be computed.
While Helix has been used to completely replace rebar in suspended concrete, we don't allow it without full-scale testing. The allowable probability of structural collapse is actually lower than getting struck by lightning. There are limited circumstances where some rebar may be required in addition to the Helix. This is what we refer to as Helix hybrid design.
The development of the Helix design model was accomplished through direct tension testing, testing of Helix distribution, and with the development of a 3-class design system that imposes restrictions on application and geometry. This ensures the design will provide the same level of structural reliability as conventionally reinforced concrete structures.
The resistance model includes the force per helix model and the model of helix distribution. The force model is constructed using a linear regression of the direct tension data. The model relates the number of pieces of helix per unit area and the compressive strength to the tensile force. The plot shown is simplified. It only shows the relationship between the number of helix pieces per unit area and the tensile force. The coefficient of variation, the second item needed for the model, is only 9%, which is very good for any concrete-related application. The distribution model itself for discontinuous reinforcement was developed in the 1980s by Wang. Testing dating back to the early 1990s established the independence of embedment angle of helix on the tensile force resistance and is included in the resistance equation. There is, however, a limit to that independence. Only helix at angles greater than 30 degrees in either axis relative to the load are active. The coefficient of variation ranges from 25% at low dosage to 2% at very high dosages. This was verified through petrographic analysis conducted at Element Labs on specimens with various helix dosages, as shown in the photo. In addition to measuring the variability, the distributions pass statistical tests for randomness. The The Helix design class system breaks applications into 3 classes depending on the consequence of failure and the geometric constraints. Class A is limited to shrinkage and temperature resistance applications, like slabs on grade. The structure is fully constrained by the soil. Collapse is not possible, so the consequence of failure is very low. Class A designs have an average factor of safety of 3.7. The average factor of safety is computed in the calibration process by comparing over 120 actual field tests of Helix reinforced concrete to values predicted using the Class A resistance function. Class B is for structural concrete, but it's limited to soil-supported structures, arches, or walls with lateral supports less than 24 times their thickness. Designs in this class are not allowed to exceed the tensile strain limits of the proactive phase. The objective is to keep the concrete strain low to minimize the formation of visible cracks. Class B has an average factor of safety of 5. When we have suspended concrete, or when the strain limit is exceeded, we use Class C, which allows design in the full stable tensile region up to 1,000 microstrain. This class has an average factor of safety of nearly 9. In suspended horizontal applications, minimum structural rebar is required along with the Helix. The rebar provides strain control and prevents the design from entering the pull-out phase.
With the design model complete, the next question is, if Helix is not mentioned by name in my design code, how can I use it? Is it approved? The simple answer is yes. All codes that we're aware of have performance-based alternative design allowances. In an effort not to stifle innovation, even the most prescriptive codes have a statement that says that you can use alternative methods and materials if you can show that they perform at least as well as the design provided in the code. The American Concrete Institute recently clarified that Helix may be used in any application provided it meets this requirement. To make this process easier for you, we worked with Uniform ES, an ISO certified product reviewer, to review the entire design approach and all the data and compile it into a short design manual. The design manual is referred to as the Evaluation Service Report, or the ESR. It provides everything required by the building codes in over 90 countries to allow the approval of Helix. To use Helix, it simply needs to be added to the drawings as an alternative design. Uniform ES provides assurance to the building official who has the final approval authority that Helix meets the performance criteria of the code. The Uniform ES report provides instructions, applicable restrictions, and several design examples, as well as the quality control requirements for using the product. It may be downloaded directly from the Uniform ES website or from our website. After reading the document and working some of the examples, an engineer can be designing with Helix without spending days going through the data and test results. I just want to emphasize that we're completely transparent. We're happy to provide any of the detailed information you would like to see. Also, Uniform ES is available as a resource for building officials. The building official can call Uniform ES directly for assurance that Helix meets the code requirements.
The Helix design method should be very familiar. The first step is not even an extra step. It's the step you normally do when designing with rebar, which is to determine the amount of tensile demand in your application. This is simply the amount of steel that is required for whatever application you're considering. If we're looking at a section in bending, what this means is the area of steel that you would provide on a nominal basis without the resistance factor applied at the center of the tension zone. Remember, Helix provides constant tensile resistance regardless of strain. In essence, this gives you a tensile stress block underneath the neutral axis, which can be idealized as a single piece of rebar at the center of the tension zone. Once the rebar is known, a table is used to determine the number of pieces of Helix required to replace the rebar. A second table is then used to determine the Helix dosage.
Keep in mind that there's some additional checks that we'll do to ensure stability and that the strain limits are satisfied for the design class we select.
Let's just look at an example to illustrate the process. We're going to consider a 6-inch thick wall made of 4,000 psi concrete with a reinforcement ratio of 0.0025. It's laterally supported at both the top and bottom at 12-foot spacing. which equates to 24 times the wall thickness. The rebar is placed at mid-depth and is standard grade 60 bar. The evaluation report includes a flow chart to aid in class selection. We can quickly move through it. The example project is not soil supported or a slab on metal deck. It's a wall with lateral supports at 24 times the thickness. This leads us to Class B. Now that we have selected a design class, we can begin. We start by computing the nominal area of steel. This is the resistance factor applied in the original design times the area of steel. In this case, we calculate 0.18 square inches per foot. We then take this number to Table 1, Column 1 of the evaluation report as shown here. We read the value in the table that corresponds to this area of steel, Class B, and the compressive strength of the concrete, in this example 4,000 psi. The result is 237 pieces of Helix. We use Table 2, shown here, to compute the Helix dosages. Start by computing the Helix per unit area. For the purpose of this example, we assume the area in tension is equal to the gross section area. In reality, this would be slightly less. In flat plate-like structures like walls and slabs, the neutral axis depth is typically very shallow, so this assumption is not too far off. Standard practices may be used to compute the actual neutral axis depth and tensile area. Doing this will slightly increase the dosage. For this example, we divide the number of Helix required, 237, by 72 square inches. We take the result, 3.3 Helix per square inch, to Column 1 of Table 2 and read off the dosage corresponding to Class B and 4,000 psi. The result is 20 pounds per yard. And we're done. Well, not quite. We have to complete the strain check to ensure the design meets the Class B requirement. If it doesn't meet the requirement, we'll need to add rebar or use Class C design to control the strain in the structure. The strain check is done by computing the average tensile strain. Divide the tensile stress in the concrete by the modulus of elasticity of the concrete, EC. We use Table 3 along with the number of Helix per unit area computed previously to get the tensile stress of the Helix concrete. For this example, we get 193 psi, and we divide that by 57,000 times the square root of F prime C. When we multiply the result by 10 to the 6, we get a microstrain of just 54. The limits are published in a table in Section 5 of the evaluation report. They're derived based on the strain at crack formation versus the Helix per unit area. In this case, the limit is 96 microstrain, so the design is okay for Class B.
Why would you specify Helix in a project for your client? Ultimately, engineers are providing a product to their client. Unfortunately, if you're bound by the codes, you're offering in essence a commodity. As an engineering firm, using Helix provides an opportunity for you to provide your client with something that's better, as well as something that actually saves time and money for them during construction.
This table is a summary of the improvements in performance with Helix. Shear increases by 250% because Helix is active at all angles. The modulus of rupture of the concrete increases by 10%, and the durability, or the concrete's ability to resist repeated beating, increases by 50%. As a general rule of thumb, Helix provides a direct cost savings of 20%. The cost of Helix is about the same as rebar. The 20% savings comes from the reduction in labor. More significantly, perhaps, is the savings in time. Our customers tell us that they save 1 day of construction for every 10,000 square feet or 900 square meters of rebar replaced with Helix.
One of the most common questions I get is, how does this stuff finish? Because of its shape and size, Helix settles below the paste and you don't see it once it's in the mix.
It's very easy to finish, requiring no special methods. Helix reinforced concrete is finished with the same standard methods as plain concrete. Pictures are not great for this. Short of visiting one of our many construction sites using Helix, we invite you to visit our YouTube channel. You can view footage of several Helix installations and the entire process. You'll find that there are no special methods that are being used, and in fact, you can't even see the Helix in the concrete at each stage of installation.
We invite you to specify Helix on your next project and provide your client with an improved product while saving them valuable time.
It's as simple as designing based on the principles we just discussed and noting Helix as an alternative on your drawings. If you require more detailed specification documents, you can download a CSI formatted Helix specification template from our website. We do warranty the tensile resistance quoted in the valuation report with one catch. We require you to submit your design to us for checking prior to construction. Details of the warranty are in the CSI specification template. Your designs can be emailed to us or submitted on our website. You may also use our Helix Dosage Calculator app available on all smartphones and tablets, where you can get an estimated dosage instantly and proceed to submit the project details to our engineering team.
While we hope you will want to design with Helix on your own, we're available to help. If you send your project requirements, we'll respond within 24 hours.
At no charge, our engineering team will complete the design for you and provide you with a detailed submittal with step-by-step calculations that are fully compliant with the evaluation report. And there's no obligation. With that, I appreciate your time and attention, and I look forward to working with you as you begin to work with Helix.